All right, video number 4, the last of chapter 0, section 3. This time we're talking about the number E. You say, wait, that's a letter. I say, yeah, I know, but actually it's a number. So the big idea is here, continuously compounded interest formula. That's something you might have heard before. And the only vocabulary is that number E. So let's get rocking and rolling and talk about that number E. So we saw in the last video that as the number of compounding periods went up, as we went from annually compounded to quarterly compounded to monthly compounded, the result or the amount of money in the account at the end of the investment period went up. So that really means to us, the more the number of times you compound in that year, the greater the amount of money you have at the end of the period. Well, as it turns out, that does not just increase without bound. You can't just say, well, I'm going to compound every second, and the next person says, I'm going to compound every half second. It turns out that there is a limit here, and that limit has to do with that part that we multiply by, the 1 plus r over n. So this portion of that formula, the 1 plus r over n raised to the power of n, as it turns out, as n goes to infinity, as n goes to infinity, this thing goes to e to the r. So what is e? You're probably asking now. Well, we're going to get into E a lot when we get into the actual calculus. This being chapter 0 in a pre-calculus section, what I want to do right now is just kind of get an idea graphically as to what E represents. So what we're going to do is look at this as 1 plus r over n to the n. We're going to turn that back into something that we could graph as a function. So we're going to look at it as 1 plus 1 over x to the x. So let's pretend that that rate is just 1. And what happens as x grows large? And we can explore this in the Desmos graph that I have linked here at the bottom. So let's clear the screen, move back to the mouse, click that Desmos link, and change our focus over to the Desmos tab. All right, so the purple graph that you can see here represents what we were just talking about, that interest rate portion. And we want to take a look at what happens as the number of compounding periods gets bigger. So this X value here, we've talked about quarterly compounding, yearly compounding, monthly compounding. If that just goes out into infinity, daily compounding, hourly compounding, secondly compounding, and then just every single moment of every single day, if you compound, what happens? Well, watch the graph. It flattens off pretty quickly. It does not grow without bound, and it seems to kind of flatten off somewhere between 2 and 4, definitely closer to 2 than 4. So over here on the left side in a table, let's watch what happens as x gets really big. When x is 1 compounding period, that number goes to 2. 5 compounding periods, 2.488. But as x now goes from 10 to 100 to 1,000 to 10,000 and 100,000, this seems to sort of level off right around 2.718. And so when I say E, I'm referring to this number, 2.718. So let's head back over to our slideshow, change the focus back over here, and get our pin, and let's put that down there. That E is approximately 2.718. There it is. All right, so let's go to the next slide. And it's our continuously compounded interest formula. So it says if you're going to invest some money and it's not compounded yearly or quarterly or monthly, it's compounded continuously all the time, If you begin with principal E or P and you earn some annual interest rate R and it's compounded continuously all the time, then the value of that account in T years is given by this formula: P, your principal, times E to the R, all to the power of T, or since power raised to a power you multiply, we can look at that as P E to the R T, or PERT, as you guys probably know it. So here's an example. Last part of this whole entire section: Emily deposits $2,500 in an account earning 5.4% annual interest. Find the value of the account in 10 years if the interest is compounded daily and continuously. Well, what happens if it's compounded daily? Here's what we're looking at. This is not continuously compounded. It's 365 compounds. So there's our principal times 1 plus the rate divided by the number of compounds in that year, all to the power of the number of compounds times 10 years. And this turns out to be a good sum of money, about $4,289. Let's get that down there. $4,289 and some change, about 85 cents. So what happens if you change that from compounding daily to compounding continuously? Well, your formula is a lot quicker. I can tell you that. It's that principal P 2,500 times E to the power of 0.054. There's your rate times 10 years. There's your time. And this one turns out to be actually a really similar amount of money, but it is more money. This one comes out as $4,290. $4,290, and again, some change, about 2 cents. So the difference between compounding daily and compounding continuously, not much. In this case, the difference here is only about 17 cents. So the takeaway here is, yes, as you continue to increase those number of compounds in a year, your exponential growth does get larger. However, that exponential growth does not grow without bound. It does flatten out, and it flattens out at a number that we're going to call E, which is approximately 2.718. All right, answer the question that follows, and you are done with this section. Nice going.